Hello everybody, I am Saul Dominguez Garcia. I'm going to talk about this research named a study of the corrosion behavior of an intermetallic iron aluminum nickel alloy in acid solution. The authors of this work are Luis Alberto Blanco Sánchez, Saul Dominguez Garcia, Elpidio Jiménez Madrigal, and Marco Antonio Espinosa-Medina. We are from Universidad Michoacana de San Nicolás de Hidalgo. Addressing the need for new materials, specifically metallic alloys with improved physical, mechanical, and chemical properties compared to the steel alloys currently used in the industry for manufacturing tools, structures, and machines, it is necessary to investigate the performance of alloys obtained by combining frequently used metals such as iron, aluminum, and nickel. This combination can enhance the properties of the resulting materials. This work presents the study of the corrosion behavior of an alloy of 50 atomic percent of aluminum, 25 atomic percent of iron, 25 atomic percent of nickel with 0.5 weight percent of silver in acidic and alkaline solutions methodology. In this way, the corrosion study of cast aluminum, iron, nickel-based alloys in acidic and alkaline solution was carried out using electrochemical techniques. The alloy was obtained by melting pure metals in a vacuum induction furnace. In the first step, the iron and nickel were melted, and then the aluminum was added. This base alloy was recast to add high purity silver content and cast into a metallic mold. Samples with dimension of 1 per 1 per 0.5 centimeters of alloy were cut by wire electro-erosion, polished with sandpaper, and cleaned in an ultrasonic bath with methanol. Some samples were polished to a mirror's finish with 0.5 micrometers diamond particles and micro-etched to be characterized by a scanning electron microscopy and X-ray diffraction. Additionally, Vickers micro-hardness measurements were performed applying a load of 200 grams. The electrochemical cell was set up with 3 electrodes, Calomel standard electrode, graphite bar, and alloy as reference, auxiliary, and working electrodes, respectively. The solutions were prepared with water, hydrochloric acid, and sodium hydroxide to reach pH values of 4, 6, and 8. On the one hand, potentiodynamic polarization tests were conducted by applying a polarization potential range from less 500 to plus 1500 millivolts versus the open circuit potential with a scanning rate of 1 millivolts per second. From the potentiodynamic polarization curves, anodic and cathodic slopes, which are beta 8 and beta C, were obtained using the intercept method. On the other hand, the polarization resistance measurements were carried out in the range of plus and less 15 millivolts versus the open circuit potential, and a scan rate of 1 millivolts per second every 15 minutes for 24 hours. From the linear polarization resistance results, the corrosion potential, polarization resistance, corrosion density, and corrosion rate kinetics were estimated following the standard method. Additionally, after the electrochemical test, the surface of the corroded specimen from the linear polarization resistance assessment were analyzed by scanning electron microscopy and energy X-ray dispersion spectroscopy to characterize corrosion products formation. In the results section, the characterization of the alloy showed two phases in the materials, a predominantly homogeneous microstructure with grain size ranging from 50 to 100 micrometers, and a minor segregated phase with distributed homogeneously with the microstructure, which are lighter grains, while the minority phase was primarily presented at the boundary of the larger grains. According to the X-ray results, the diffraction patterns indicate the presence of an aluminum-rich solid solution phase, which is beta in this graphic, with a B2 ordered BCC structure, which is sigma in this graphic. Additionally, a series of 15 measurements of Vickers micro hardness were performed along the surface of one sample, yielding an average value of 591 HB with a standard deviation of 11. In the electrochemical measurements, by one side, from the potential dynamic polarization measurements, 3 Tafels curves were obtained and corrosion parameters were calculated by intersection method. These results are listed in this table. This data indicates the largest corrosion density was for acid media at pH 6, which is blue line. This value is 0.989 microamperes per square centimeter, and the most negative corrosion potential was for alkaline media at pH 8. In this table, the Tafel slopes are also listed, these two columns, beta 8 and beta C. By the other side, from the linear polarization resistant measurements, 3 profiles of polarization resistant and corrosion potential were obtained. Then, using the Tafel slopes, 3 profiles of corrosion density and corrosion rate were computed, one for each pH level. The comparison of kinetic corrosion rates indicate the acid condition at pH 6 as the highest and the other two conditions as the lowest. These rates are 0.15 micrometers per year for pH 6 and 0.05 micrometers per year for the other two pH conditions. You can see here and here. The expected anodic and cathodic reaction are the oxidation of aluminum, iron, and nickel from metallic state, the reduction of water molecules producing molecular hydrogen, and the reduction of oxygen with water producing hydroxide anions. In addition, the expected reaction of the corrosion byproducts are the formation of aluminum hydroxide, nickel oxide, nickel hydroxide, and of course, iron oxide. The micrograph of the corroded surface of the alloy showed generalized corrosion at all 3 pH levels, and at pH 4 the alloy presents evidence of some pitting. You can see in this picture here. However, most of the current density contribution was associated with uniform corrosion. It is suggested that future investigation study the corrosion mechanisms used in other electrochemical techniques for this alloy in both acidic and alkaline media. In summary, the low corrosion rate values observed in all 3 conditions were associated with the passive corrosion products layer, primarily composed of aluminum hydroxide. From the lab results, this research gives the following conclusion. The microstructure of the alloy consists of 2 phases, a solid solution phase as the matrix and a segregated intermetallic phase. The matrix was composed of an aluminum-rich solid solution phase with a B2 ordered structure and a silver-rich intermetallic phase observed at the grain boundaries. The microstructure exhibits an average Vickers micro hardness value of 591 HB. The effect of pH on the passivation behavior against corrosion of the aluminum, iron, nickel with silver alloy correlate with iron and nickel contents within their respective potential pH region. The corrosion rate at the 3 pH levels indicate low electrochemical activity on the alloy surface, all below 0.19 micrometers per year, with a value of 0.05 micrometers per year observed at pH 8. This compared to the widely accepted maximum permissible corrosion rate in the industry of 0.125 millimeters per year. The corrosion behavior was attributed to the growth of a passive thin film at the initial state of corrosion, primarily due to the formation of aluminum hydroxide. Some important reference for this research you can see in the text box of this video. That's it.